Okay, let's get started. We're now in Unit 13. We're going to discuss what's called the central limit theorem, and in a later video we'll cover the confidence interval for the mean. So to kind of highlight the central limit theorem, we're going to show you an example. But before we get to the example that will demonstrate the central limit theorem, we are going to discuss some key definitions. The first definition deals with population. So as we move into the latter part of statistics, we're going to be working with what are called populations, and the population is all members in a specific group that you wish to study. So it's all members in a specific group that you wish to study. So an example would be all the ages of students attending Fair Oaks Private College. So we're going to think of three other types of populations that you can study. I'll just work on one of these. One of these can be all the stray dogs in Barstow, California. Okay, so that could be a population that someone may want to study. And there's certain characteristics. Is the population increasing, decreasing? What type of diseases does this population have? So those are typical characteristics that a person may wish to study about such a population. So think of two others that you may wish to study. We also have what's called a sample. So typically when you have a population, it's almost impossible to study every object in that population. So what we do is we collect a sample, and then that sample will be used to represent the entire population. But when we collect the sample, we have to do it in such a manner that we will avoid any type of bias. So typically there's some procedures that we follow to randomize the objects that are collected in our sample. And we do have another example here. So the example would be going back to our stray dogs. Let's just say that we collect, we'll say the sample is 40 stray dogs that are randomly selected from Barstow, the population of the Barstow, California dogs. So that would be our sample that we're going to work with. And just try to think of another sample. Now we're going to transition into working with an example of the central limit theorem and how it operates. So let's start with, assume that we have 800 students who attend Fair Oaks Private College. The population we will study will be the ages of the 800 students. And so if we calculate, let's say we know the average age of the 800 students. Let's say that the average age is 25 and the standard deviation is 4.7. This is for all 800 students at Fair Oaks Private College. So if we were to collect a sample of 5 ages from the population, and we list them below, we have the ages here. Let's compute the mean. Well, if we compute the mean of these 5 values and round to a whole number, as it states here, we would get the age 28. And so how much does the mean differ from the actual mean? Well, it differs by 3 years because the actual mean is 25, right? So our sample, no matter how we collect our sample, there's always going to be some sampling error. So there's always going to be a difference between the sample mean and the population mean. And we have to take note of that. Now, if we repeat this process for 11 samples of size 5, so now we're not just going to work with one sample, we want 11 other samples. Let's go ahead and take a look. So I've already did the work. Here we have 11 samples. Let's put this 11 samples of size 5, and so we have 5 different ages that are randomly selected from our population of 800 ages. And for each of these samples, we're going to compute the sample mean like we did in our previous example. In fact, that example is right here. That's the first of our samples. The average age was 28. And all the other samples, we have other sample means. There's always, every time we collect a sample, there's always going to be typically a different value. There's some values will repeat, but typically you're going to get different values. And that's called this, and they're all going to be slightly different, but somewhat close to the actual mean of 25. So if we were to plot these sample means and look at the distribution, we would have the following shape. Doesn't really say much. Somewhat symmetrical. And it turns out we can calculate the mean of all the sample means. If you just, all you do is you add them all up, divide by 11. That mean is 25. We can also calculate the standard deviation. It's 2.3. So it's better to have more than one sample, obviously. And we also want to increase the number of samples that we collect, but also we want to increase the size of the samples. So in our next example, we're going to increase the number of samples. Here we have 11 samples. Now we're going to look at 50 samples of size 5, and we're going to calculate 50 sample means and graph them. And so this is what the graph will look like, a bar graph of 50 sample means of size 5. The mean still remains 25. The standard deviation is 2.1. Now finally, instead of just working with the sample size of size 5, we're going to change the sample sizes to size 30. And we're going to graph all the sample means, and we're going to compute the mean and standard deviation. And what ends up happening is that our sample mean will take on this shape. Ultimately, what should happen as we increase the sample size, when we graph all the sample means, it will take on a normal shape. Okay, so that's going to lead to our central limit theorem. It just states that as more samples are collected and the sample size, we'll just say the sample size is increased, then the shape of the distribution of sample means, all of these sample means that we are plotting, will become normal. So it will have, it's not going to become a normal distribution, it's just going to be normally shaped. Okay. And it turns out that the mean of the distribution of the sample means will be the same as the population mean. So in this case, it's 25. The standard deviation of the distribution of sample means, however, will change. It's going to be smaller. It's actually the standard deviation divided by radical n. So in our example, we found that it was 4.7 divided by radical 30. That's going to be 0.85. So that's how we came up with 0.85 and 25. So we have this distribution of sample means. It has a normal shape. It has mean mu, but now the standard deviation is sigma over radical n. So we have to modify our z-score. So we have a new formula for the z-score when we work with the distribution of sample means. The z-score is x bar minus mu divided by, so that's just similar to our previous z-score formula. It's like x minus mu over sigma, but now each value is an x bar value, and we don't have sigma because sigma is now sigma over radical n. So this is our new z-score formula that we're going to work with. Okay, so let's look at an example here. Let's say the mean age of students at Fair Oaks College is 25 and the standard deviation is 4.7. If a sample of 39 students is collected, compute the probability that the mean age of the sample will be less than 24. So I like to assign variables just to clarify what each variable means given this type of problem. So remember, the mean That's the average of your population. It's represented by mu, and that's going to be 25. The sample mean, that's the mean for the 39 students that we're collecting. It's represented by x bar. So remember, mu is the population mean, the mean for all 800 students at Fair Oaks College, and x bar is the sample mean, the mean for the 39 students. And as we saw, there's always some type of difference between the sample mean and the population mean. So that's 24. N, that's your sample size, that's 39. Standard deviation, sigma, that's 4.7. And then when it says less than, we have to think of this symbol. This symbol means less than. So we're saying that the average age is less than 24. So and since our sample size is greater than 30, we can go ahead and graph the normal distribution. The mean is at the center, it's 25. Sigma is 4.7, N is 39. And just take note, anytime you're provided with an N, that's kind of a clue that you're going to be working with the central limit theorem. And we need to find the probability that the mean, because every value on this axis is an x bar value, that the mean of the 39 students will be less than, the mean age will be less than 24. So what we need to do is we need to convert, we need the z value for 24. So let's convert our x bar value to a z value. We plug all our information in, and we end up getting a z value of negative 1.33. So that's going to allow us to look up the z value in table E. So now we turn to table E, we look up negative 1.33, and we find the answer. The answer is 0.0918. So the chance that the average age of the 39 students will be less than 24 is 0.0918, about 9% chance. And I have a couple of other examples for you to try. Let's go ahead and look at another example, just to kind of clarify the concepts. Let's assume time spent studying for a remote learning course in mathematics is normally distributed. Here, when it says that, we don't have to worry about the distribution. It is normally shaped. If the average time spent studying by community colleges students per week for a remote learning mathematics class is 6 hours, and the standard deviation is 2.4 hours, then find the probability that for a sample of 35 students, the probability, we'll just put the probability will be less than 5.6 hours. So using the chart I mentioned, mu is, once again, the mean of the population. That's 6 hours, right? So that was given. Sample mean, x bar, that's 5.6 hours. That's the sample mean for the 35 students. N is your sample size, that's 35. The standard deviation is sigma 2.4, that was given. And once again, we're looking for less than. So x bar is less than 5.6. So if we were to draw the normal distribution, we're looking for less than 5.6. So that's about right here. We convert, and what I like to do when I make these conversions is I like to take the reciprocal of the denominator. So sigma over radical n, you can change that to radical n over sigma times that difference. Plug the values in, we get negative 0.99. So negative 0.99, that's our z value. We look up that z value in table E, it's 0.1611. So there's about a 16% chance that the average time spent studying for the math class is that it's less than 5.6 hours for 35 people is about 16.11% or 0.1611. And that is section 2.3.